Okay, so section 9.2, pre-calculus 30, we're talking about analyzing rational functions, okay? So remember, a rational function is where we have a polynomial in the numerator on top and some kind of polynomial in the denominator. We don't usually talk about rational functions where the polynomial is just a constant. We're talking about when we have an x in the denominator, okay? That's what we're talking about with these rational functions. So this one right here, okay, this is looks like a very complicated function, and it appears that the graph is very simple. It looks like a straight line. We talked a little bit about this in 9.1, right? That the way the graph looks sometimes is because you can simplify the original equation. And so if we take a look at this, you might remember this, but I'm going to rewrite this up here. And what we're going to do is we're going to factor the top. And so that's going to become what? What are two numbers that multiply to positive 6, add up to negative 5? That's going to be x minus 2 times x minus 3. That's this trinomial factored. On the bottom, we have x minus 3. Okay? So what we see is that when we factor, we can actually simplify this function into y equals x minus 2. And so this is why the graph ultimately looks like a straight line. You see that? This is a linear function right there, y equals x minus 2. It has a slope of 1 and an intercept of negative 2. So start at negative 2, go up 1, over 1, up 1, over 1, up 1, oh! But we have this little thing here. So this little gap, and we talked about this before actually as well, sometimes when we have restrictions for x. And so the reason why this looks like a straight line is because of the simplified version of this rational function. That's number one. The reason why there's this gap is because if you look at the original function, x cannot equal positive 3. If x equals positive 3, the value of y is undefined. Okay? That's why there's no value for y at this point. Okay? So when we're taking a look at the graph of a rational function, what we need to do is we need to do a few things to graph it, but also to make sure that we don't miss any asymptotes or gaps in the graph. So when we're analyzing these, or let's say we're graphing these, okay, so here are some steps that I'd like you to follow. First of all, what you want to do is you want to take a look at the original function and you want to note restrictions, okay? So step 1, note restrictions. And that comes from the denominator usually. So x minus 3 cannot equal 0. Okay? And that means that x cannot equal positive 3. So step 1, note restrictions, because when you start to simplify, you might forget what values are restricted. Okay? And so that's important. So note restrictions, number 1. Number 2, factor the numerator and the denominator fully. And that's what we did in this step right here. We factored both the numerator and the denominator as much as possible. Show it as factors. That's step number 2. Step number 3, okay? Note restrictions again. If you're able to factor the denominator and you didn't see that there were some values for x that were restricted, then note restrictions again before you actually eliminate or divide out any factors. So note restrictions again. The restrictions are still the same in this case. And then number 4 is divide out the common factors, which we did here in this step right here. Take these factors out and then write the simplified version of the function. Okay? So those steps are very, very important. Boys, are you writing down these steps here? Make sure you're following along, okay? You'll have to save that for later, okay?
What is number step 3 again?
Step 3 is note restrictions again.
So what does it mean?
That just means, okay, I'll say it again.
Yeah.
If you had a denominator that would look like this, and you factored it, and you saw that there were a number of factors, and you didn't realize that there was restrictions at the beginning, you might have restrictions at the beginning. So for example, if you had, this is just an example, if you had this, x squared minus 5x plus 6, and you had x squared plus 7x plus 12, well, you might not see the very first step. You might not see where the restrictions are, right, until you factor. So when you factor this, right, then you've got x minus 2 times x minus 3, and then this one here is what? X plus 3, x plus 4. Then you say, oh, wait a minute, I actually have some restrictions for x. X cannot equal negative 3, x cannot equal negative 4. You might not have seen that at the very beginning. So that's why I just put that step in there again, just in case it's now obvious that, hey, there are some restrictions I didn't see at the beginning, okay? Good question, though. All right, so asymptotes and gaps. We talked a little bit about this, so let's formalize this in 9.2, okay? So if a factor remains in the denominator, sorry it's a little bit messy and now these notes are getting a little bit convoluted, but if a factor, a binomial factor especially, or just x, remains in the denominator after simplifying, this represents a, what goes in the blanks there? Who remembers? If a factor remains, once it's simplified, we still have this binomial factor. That is a what? Represents a what?
Asymptote.
An asymptote. What kind of asymptote? Horizontal or vertical?
Horizontal. Vertical, actually. Yes. X equals something. Yeah.
It is a vertical asymptote, yes. Now, notice in our above example that there's no vertical asymptotes. No vertical asymptotes. Why? Because this factor that was down here did not remain at the end after simplification. Okay? So if it's still there at the end, we're going to have a vertical asymptote. Okay? But if it's not, if it's gone, then we have, well, that's what the next point is. If a factor gets divided out, that factor represents a blank blank. Represents a, not an asymptote. What does it represent here in this example? It's a restriction. Yes, very good. A gap, discontinuity. Discontinuity. So remember that funny word we talked about a couple days ago? Discontinuity. Discontinuity. That's the way you want to say it, probably. It's a gap, discontinuity. So what that means is the line goes along, and then there's a bit of a jump. There's a bit of a space. So A, it's discontinuous, and it's not discontinuous because there's a jump like this. So some graphs, the line is horizontal, then all of a sudden it jumps up here. Or it's not discontinuous because there's an asymptote. It's discontinuous because there's just a tiny little gap. A gap discontinuity. Okay? So, sorry these notes look quite messy here now that we've done all this fiddling around, but hopefully you're understanding those first of all, the steps in graphing and also in recognizing where the asymptotes are. Okay, so let's take a look at this question right here, which I think might be question number 1 in your assignment. Looks fairly familiar. So yes, this is number 1 in your assignment. So we'll pop back to the notes here. It says this: the graph of the rational function y equals x minus 4 over x squared minus 6x plus 8 is shown. Okay. Oh goodness, my computer's struggling. Okay, so it's shown here. Okay, what do we want to know? Well, oh, looks like I have some answers here. Okay, so let me get rid of some of that. Okay, get rid of those answers for now. We'll do that together. So copy and complete the table to summarize the characteristics. Okay, so we can look at the graph, we can look at the function, we can do some work on the function algebraically, and we can come up with all sorts of characteristics for this graph. So let's see. Non-permissible values. All right, those are the restrictions, right? What are the restrictions on x? And restrictions on x come when we're trying to take the square root of a negative, that's no good, or when we're trying to divide by 0. Those are the two popular ones. So obviously there's no square roots in here, but there could be some restricted x values here. So what we should do is we should factor the denominator to c. So what is this? What two numbers multiply to 8 and add to negative 6? Negative 4 and negative 2. So that's how this trinomial is factored. Negative 4 and negative 2 add up to negative 6, and negative 4 and negative 2 multiply to positive 8. Okay? All right, so before I do any dividing out or any simplifying, let's just take a look at this. Are there any restrictions on the x?
Yes.
Yeah. X cannot equal what?
4.
Positive 4. Okay, so x cannot equal positive 4. And what else?
2.
Positive 2. Yeah. Hopefully everybody sees that. If you let each of these kind of not equal 0, this cannot equal 0, so x cannot equal positive 4, and so on. That's how you do that. Okay? Take each factor separately. All right, whoops. Erase, erase. All right, so the next line says, feature exhibited at each non-permissible value. Okay, so what is the feature? Okay, so this is a really good one because it combines an asymptote and a gap. Okay, so at x equals 4, we have a what? What kind of discontinuity is this? That's a gap. Okay, so a gap, and however you want to write that. Gap discontinuity. I'll just abbreviate there. Now, we can see that from the graph. Does anyone see why that is from the equation? So I can see that at x equals 4, there's going to be a gap discontinuity because, someone finish that sentence for me. Okay, the factor of x minus 4 divides out upon simplification. Exactly. So if it's gone, once we simplify, then that's a gap. Okay, so at x equals 2 then, obviously from the graph, we can see we have a vertical asymptote. Okay, vertical asymptote. And that simply is because upon simplification, that x minus 2 factor is still there. If it's still there, then this, see this graph really looks like this. That's what this graph looks like. It's a 1 over x graph shifted 2 units to the right. So this asymptote that should be at x equals 0 is shifted 2 units over. You see that? So all this is lining up. But you see, if you just look at this, you wouldn't have any idea if you have any gaps. So that's why you have to notice what the gap discontinuities might be before you simplify. Because this x minus 4 is totally gone. All right, here's an interesting one. What's the behavior near each non-permissible value? Okay, now this might take a little bit more space than we're given here, but let's just talk it out. So near x equals 2, okay, the graph on the left races towards negative infinity, or it gets very, very small, okay? And on the right side, the y values race towards positive infinity, or get very, very large, okay? So this is, again, this is the way I would say this. Left of x equals 2, y values, and you're going to have to do this on your assignment, so you might want to write this down. Left of x equals 2, y values approach negative infinity. Right of x equals 2, y values approach positive infinity. And again, positive infinity is just like the numbers get super, super high, right? Approaches the highest number we can imagine.
Mr. Robertson or Mr. Kerr,
So,
call 274. Mr. Wade
what about
Robertson
around the
or
x
Mr. Kerr,
equals
please call
4?
274.
So x equals 4, the behavior near this value, okay, the graph gets very, very close to what? So again, this is actually, we're getting into calculus language here, okay? It's a pre-calculus class. So we're talking about, this is calculus language, approaching infinity. That's calculus. We use that a lot in calculus, okay? Now this one here, we're gonna talk about this. What value, what y value does the graph seem to approach as x approaches 4? So for example, as x approaches 4 from the left side, what do the y values seem to get closer to? So there's 1. Well, careful now. What do the y values seem to get close to when x approaches 4? it actually approaches this little gap, doesn't it? Because you see, we've got 1 here, and we're going down to, looks like what? Yeah, so this is 1. Sorry, it's really thick because I've zoomed in. Okay, so as x approaches 4 from the left, the y value seems to approach 1/2. You see that? This value right here is 1/2. What about as x approaches 4 from the right? So there's a y value, there's a y value, there's a y value. What does it seem to approach as x gets closer and closer to 4 from the right side? The same value of 1/2. So you see how the graph is kind of coming like this? The graph is approaching y equals 0.5, 1/2. Okay, so again, this is a little bit of calculus language I want you to kind of get used to. So here, let me just, whoa, that's 100%, eh? Okay. Okay, so as x approaches the value of 4, y values approach what? What would we say? Approach y equals 0.5. Okay, so I realize this is sort of new language for you, new way of kind of expressing this. You may just want to write a little couple sentences and describe it, maybe in different words. I think that you should get used to using these type of words. Infinity. X approaches a certain value. That means it gets infinitely close, but doesn't actually touch it. Those terms are important. Okay, so I guess that's the behavior there. And the domain. Okay, well the domain's pretty easy. Domain is all real numbers except for x equals 2 and x equals 4. And you can write that in the negative if you want, like domain x cannot equal 2 and 4, and then it's all real numbers other than that. So however you want, that's acceptable. Just x does not equal. I'll accept that. You can express it in the negative there. Okay. Any questions about this? This is the bulk of this section here. Oh, well, does it ask for range, or do I not have it on there? It does ask for range? Okay, no problem. Are there any values, y values, that are inadmissible, that are not, like there's... okay, so y equals 1/2. Okay, so it looks like there is no y equals 1/2 because of this gap. Very good. Are there any other y values? All right, so the range, what do we know? X cannot equal, y, range, y cannot equal 0.5. And what else here? Look at the graph. Y cannot also equal 0 because it's a horizontal asymptote there. Yeah. So y can't equal 0.5 or 0. But all real numbers other than that. Okay? Okay, was there anything else in that question that I missed that I didn't get on the screen? Okay. All right, so that's the bulk of the lesson right there. Question number 1. So vertical asymptotes, gap discontinuities, taking an equation, noting restrictions, graphing, make sure you identify your asymptotes, and yeah, any questions? So here's your assignment. 1, 2 AC, 3, 4 AC, 5, 6, and 11. That's your assignment for today. And I'll show you that textbook here in case you get home and you don't have your textbook with you for some reason. There's one that we did. There's 2, 3.
Frozen.
It's mainly for you watching the video, not for you here now, so because you have your textbook now. So, but thanks. There's 4 and 5. Oh, 5's tough to get in there all in one. And here's 6, match the graphs. Tough to see that all at once. 7. So there's extra questions here on the textbook. You can do as many of them as you can to practice. Anybody recognize this from physics? Have you guys been to the lenses here yet in that class?
Oh no. That's the last.
Painful? Painful memories?
What? I just remember pigs. Invisible pigs that were visible.